Hi guys, welcome to my new video. In this video I'll be showing you about AVL tree. So as all of you might know, AVL tree is actually a type of BST. So let's start explaining AVL tree with the help of this BST. So let's consider a parent number. This is the parent element over here. So let's consider a parent number uh, like 10. Okay, and then the specialty of BSC is like on the left side, and the number should be smaller than this parent element, and on the right side the number on the right side should be greater than this parent element, is 10. So on the left side, let's consider another number like 7, and which is lesser than 10, and on the right side let's consider another number like 15, which is greater than 10. And in the same way, let's write another number on the left side of this 7, like 5, which is smaller, just like the previous rule. And on the right side, let's take another number greater than 7, like 9. Okay, the same thing happens over here also. So on the left side, it's a 13, and on the right side, it's an 18. Now, this is a perfect BST, like which is an AVL tree. Okay, now you might be thinking what's the difference between BST and an AVL tree. Okay, I'm gonna explain that now. So over here, everything looks fine, everything looks balanced, neat, clean, except for my handwriting. Everything looks fine. And then what if I draw an extra node like this on the left side? What happens then is like, if I draw 3 over here, just like this, now it feels like it's not that correct, right? Because it looks something different, like it doesn't look neat. So what if I add one more node, like let's add one more node over here, and then blah 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 blah. Okay, and then let's add a number. Since it's on the right side, let's add a number like 4. Okay. Okay, now this 4 is greater than 3, but then if you look the whole thing doesn't look good. So now actually we have added impurities. This impurity is called the unbalancing factor. So like if you take 18 over here, there's nothing on the left side or right side. So the balance factor of 18 is 0. And it's the same over 9. It's the same over 9, 13, and yeah, 9 and 13, because there's no other elements branching from there. And it's also the same over 4, because there's no other element below that. So all of them have the same balancing factor called 0. Well, the balancing factor of 15 is also 0, because there's one over here like 13, and another over the right side called 18. So if you consider one element is over right side minus another element over the left side 1, so 1 minus 1 gives you 0. So it is 0 over here. It's the same over 7 also, because on the right side we have got one element 9, and on the left side we got another element 5. So when we subtract the number of elements on the right minus left, like 1 minus 1, 1 minus 1, we get another 0 over here. So we got another 0. And then in the parent also, the root element 10. Here also on the left side we got 7, and on the right side we got another element 15 to compensate the 7. So the balance factor is 0, but it all changes over 5 and 3. So if you take 5 over here, we got 1 on the left and we got nothing on the right. So the magnitude of the balance factor will be 1 regardless of the sign, even if it's minus 1 or plus 1, because some people take the left side as minus 1 and some people take the right side as plus 1. So if we take left side as minus 1, then the balance factor of 5 is minus 1. Okay, now if we are taking 3 to find the balance factor of 3, we are looking on the left side. There's nothing on the left side, so it's 0 plus. When we look at the right side, we got 4 over here. Since there's one element on the right side, we give 1 over there. So 0 plus 1 gives you 1 over here. So that is the balance factor of 3. So this is how you find the balance factor. So if you take 3 over here, 3 over here, the balance factor of 3 will be the balance factor of right side minus the one on the left side. So we got 1 over right side, so we can consider that as plus 1. And then we got nothing on the left side, so what we get is 0 plus 1, which will be 1. So the balance factor of 3 is 1. Similarly, when you check the balance factor of 5, we'll consider what is on the left side. There's one thing on the left side, so you got 1 over there, and you got minus 1 over there, plus you consider what is the number over here into negative 1. So but if there's any element on the left side, you have to multiply it with negative 1 and then add it over there. So we add minus 1 again from the left side, and then you get there's nothing on the right side, so the balance factor from the right side, the contribution from the right side is 0. So the balance factor of 5 will be minus 1 plus minus 1 is equal to minus 2. So this is the balance factor of 5. So this is where we need the application of the AVL tree happens. Like in this case, when the balance factor of 5 is minus 2, or when the balance factor of any node was greater than minus 2, we try to make changes in it such that the tree will be back again in this form, so that there won't be any other element over here which can create a height difference. Even if it creates a high difference, it can only create a high difference of just one element, not more than one. So this is how, that is the AVL tree.